So we start defining a semigroup by making a wish list. What do we like to have? What are the properties we actually would really like to have? And these are properties which typical matrix exponentials have as well. So we consider a family t larger or equal 0 of bounded linear operators on a Banach space X. And this is called a strongly continuous semigroup, or C0 semigroup. So let's move this circle there. If it satisfies three conditions, so one is t of little t plus s is t of t times t of s. This is also called the semigroup property. And then t at 0 is the identity matrix. And for all u, my goodness, another spelling here, come on. For all u, the map t maps to tt of u is continuous in X. And we will then later see that it's actually sufficient to check continuity at t is equal to 0 because of the semigroup property. If you look at continuity at any other t1, say, you can always use this identity, t of t1 plus 0 and so on, and then you check continuity at t is equal to 0. Okay. So the exponential e to the at, where a is a matrix, would satisfy all these conditions, right? So e to the a, t plus s, is e to the at times e to the as. Fine. E to the 0 is the identity, and then the map is continuous as well. So that's all good. Let's do another non-trivial example, which has to do with PDEs. So we look at continuous functions on R and consider the left shift. T of t applied to a function u of x is just u of x plus t. Okay, so it's evaluating the function a little bit more to the right, so in the end it is the left shift of the function. T is a strongly continuous semigroup, so let's check the conditions. Firstly, if I have t of t plus s applied to u, then this is the same as having u evaluated at x plus s plus t. If I apply them in order, then I do just get the same. I first increment by s, then I increment by another t. So this is item 1. If t is equal to 0, of course, then we increment nothing, and we just keep u of x. So t at 0 is the identity, and item 2 is also satisfied. And for continuity in t, we can simply compute limit t to 0 ttu, which is, of course, the limit as t goes to 0 of u of t plus x. And now u is continuous, as we assumed, so that is satisfied too. Okay, so the left shift is a strongly continuous semigroup, and the right shift would be as well. Now, for fun, just let's look at a first-order linear partial differential equation. This one here. Let's get another box. Bzzzt. Ut minus ux is equal to 0. This equation is solved by the traveling wave u of x plus t, which turns out to be our tt of u of x. So in this sense, t has to do with a PDE. T helps us to represent the solutions for this PDE. So we call it the solution semigroup for the PDE. Or if you write the PDE in this form, you could write this as ut equals ux, and then maybe this is like an operator of u, where a is d by dx. So in this sense, we could actually say tt is the operator exponential e to the t d by dx. Now, this was very quick, right? This was a very quick way to come to a solution semigroup and write it as operator exponential. So we can't be that quick. This was just a formal relation. There's a little bit more mathematics involved that we need to do. So one of the things we need to do is a technical lemma for sub-additive functions. So let's look at this. So we consider a sub-additive function. This basically means that omega of t1 plus t2 is less or equal omega of t1 plus omega of t2. And we will later see that the logarithm, for example, is such an example. Okay, then the infimum as t goes, no, the infimum of positive t, omega t divided by t, is equal to the limit as t goes to infinity, omega t divided by t. So this basically means that these functions grow slower than t. And this could be equal to minus infinity. Let us look at the proof. So we define omega 0 to be the infimum on the left-hand side of the equations. Here is some styling. Let me just make another remark for corrections. Okay, so omega 0 is the minimum value of this ratio, and we consider gamma to be bigger than omega 0. So then there must be a time t0, so that omega t0 divided by t0 is less than gamma, because the infimum was less than gamma. And now we choose a time which is bigger than this t0, which we write as n t0 plus a little rest. So we piece it together of so many t0 bits, and then we have a little rest r. So which means r is then between 0 and t0 excluded. Now by sub-additivity, we can split up the time as t0 plus t0 plus t0 plus t0 and so on, plus r, and then use the sub-additivity, and then we get this relation right here, where omega of t divided by t can be estimated by n omega t0 plus omega r divided by t. And now for this we take the limit as n goes to infinity, but by the previous definition here, as n goes to infinity, then also t goes to infinity. And in particular the ratio n divided by t converges to 1 over t0. So then let's look at the second term here, this omega r, this one is the second term, divided by t. As t goes to infinity, this goes to 0. All right? Now the first term though, the first term happens on the other side, but here you see already that this n divided by t goes to 1 over t0, so this bit here would go to omega t0 divided by t0. Even the supremum. So if I do lim sup of that term, I get omega t0 divided by t0. But now this was bounded by gamma. Gamma was bigger than this. For all gamma which are bigger than omega 0, which means the limit exists and it equals the infimum omega 0. Alright, this was really technical indeed, but now let's see where we use it for. We use it here in the theorem 8.1.2. T is a strongly continuous semigroup of bounded linear operators in a Banach space, and omega 0 is a limit as t goes to infinity of the log of the norm of t divided by t. And it turns out that this omega 0 is basically the growth rate in time of the semigroup. So for every gamma which is bigger than this omega 0, we have a constant m gamma, so that the norm of the semigroup t is bounded by this constant times e to the gamma t. So then we call omega 0 the growth rate, which then identifies the type of the semigroup. It could be exponentially decaying if omega is less than 0, or growing if omega 0 is bigger than 0. So this is very similar to, again, what we do for ODEs. We might linearize on a steady state. We look at the eigenvalues. Then we have growing eigenvalues, decaying eigenvalues. So here we find a dominant eigenvalue or a dominant estimate omega 0, and the semigroup cannot grow faster than e to the omega 0 t. Yeah, the proof will of course use this sub-additivity thing which we just derived, because the function log of t is subadditive. Okay, so log of t plus s, I can write this to be t times t of s, and so then I can estimate this by the norm of t and t of s, and then I use the subadditivity of the logarithm to get this. And t is bounded on bounded intervals, so by the previous proposition 811, the limit omega 0 exists of this ratio log of t divided by t. And for each gamma, we get this estimate. For each gamma bigger than omega 0, we get this estimate here. Yeah, and so then we just multiply by t, take the logarithm, and so we get this, as long as t is bigger than t0. Now, for smaller times, we just take whatever the maximum value is, right? We take t from 0 to t0, and then whatever the maximum is, we take this. Or if it's smaller than 1, if it happens to be smaller than 1, we take 1. So then this is our constant m gamma. And then we can estimate t by m gamma e to the gamma t. Let me go back to the theorem. So then we get this result here. So let me reiterate. So if we have a strongly continuous semigroup, then we know already that we have a growth bound for the semigroup, an exponential growth bound for the semigroup. This is nice. Let's do that just quickly for the left shift as an example. So tt of u of x is u of x plus t. Yeah, then the norm of tt will be the supremum of all functions with norm 1, ttu. And so that's the supremum of all functions which are shifted by t, u of x plus t. But that's the same. So the infinity norm, the sup norm, is equal to 1. So then the log of t divided by t will be 0. So then the growth bound is omega 0 is equal to 0. So which means the semigroup shows no growth, no decay, because it's simply a shift to the left.